Okay, so we're going to talk about asymptotes for a brief amount of time, and then we're going to get into limits at infinity, which also deal with a different kind of asymptote. Okay, we're talking about vertical asymptotes here first, though. Okay, so if f of x this is kind of to finish off our notes from yesterday, I guess I'll say. Okay, because we were talking about limits as x approaches c, they go to infinity or negative infinity. So if f of x approaches infinity or negative infinity. Okay, so this is again kind of like finishing off our notes from yesterday. As x approaches c. Okay, so if f of x approaches infinity or negative infinity as x approaches c, okay, from the left or the right, sometimes it is left and right, but it really only needs to be left or the right, though. Then, okay, x equals c is a vertical asymptote. Okay, of the graph of f. Okay. Yes, there's a p in there. Okay. So that's what we were basically finding yesterday. Every single limit that we did in our homework, all right, every single limit that we did. So for example here, number 1 from the homework, right? The limit is x approaches 4 from the right of 1 over x minus 4. It went to infinity, so that means at 4, there's a vertical asymptote, right? So let's do some examples here. So our directions are to find all vertical asymptotes. Okay, so let's see here. First one, we'll start with f of x, and we'll say that that is equal to 1 over 2 times x plus 1. Okay, like so. Now, if we look back at our homework, right, we were finding a limit as x approaches 4. And that made us go to infinity in this case for this first one, 4 from the right. Okay? Looking at this, though, right, we can kind of see that 4 is going to give us a problem, right? What's going to happen if I just were to direct substitute in 4 into my little function right here? It'll be 1 over 0, undefined, right? Undefined, okay? And that's also another kind of indicator that we get a number over 0, right? So like 1 over 0 in this case, makes it undefined, and so that kind of indicates to us there's a vertical asymptote. So here for letter A, what x value, were I to plug it in, would make this undefined? Negative 1. And so we'll say then, at x equals negative 1, right, we have a vertical asymptote. I'm going to abbreviate that, VA, okay, at x equals negative 1. Okay. If I were to actually check the limit, because really we define vertical asymptotes as by using limits, right? As x approaches c from the left or right, the function should go to positive or negative infinity. So I'll just kind of try and convince you of that here with this one. Okay, so 1 over 2 times x plus 1. Okay, so as you can see, that's kind of like, there we go, it's a little better. So we'll type that into our calculators just like that, yeah. Okay, go to our table. I'm going to delete out all these old values. Okay. So again, type that into the y equals there. We'll just analyze it with this one first, because just for the sake of seeing it, but then we'll just kind of convince ourselves. Okay. Okay, so go to our table, and then let's approach negative 1 from the left. Okay, and so believe it or not, right, this is a little tricky to do. So let me draw a little number line here for us. All right, so there's -1, there's 0, there's -2, and we go that way and that way. Okay, so what values should I type in here if I want to approach -1 from the left? Okay, -1 not 9, I would say. 1.01 or 1.1. Okay, that would be a good one. -1.001. -1.0001. You can kind of see what's happening here, right? You can see we're going to what? Negative infinity as we approach -1 from the left. Okay, now let's approach -1 from the right. Okay, approaching -1 from the right would be like what values? -0.9, -0.99, -0.999, -0.9999. Okay, here we're going to positive infinity. Okay. All right. So there you go. Again, be careful about approaching from the left hand or from the right hand side, approaching those negative numbers from the left and right hand side, because it kind of switches up the order on you and it's easy to get those confused. But anyway, there's letter A. Alright, let's try another one. B. So anyway, that just shows the limit as we approach -1, you go to positive and negative infinity, so it definitely indicates a vertical asymptote. Let's try another one here. Okay, t squared plus 1 over t squared minus 1.
From my homework.
Oh, there you go.
Yeah.
I don't know where that came from. I wonder. I'll have to take a look and see where I even wrote that down from. I wonder. Okay. Huh. All right. So here, what can we do to help us find these vertical asymptotes? Yeah, just set the denominator equal to 0, right? T squared minus 1 equals 0. Right, so we'll add 1 to both sides. We get t squared equals 1. And so we get square root of both sides, right? So we get t equals 1.
Plus or minus.
Right, plus or minus.
Yeah.
Okay, so t equals 1. We have a vertical asymptote. T equals -1. We have a vertical asymptote. Effie, what's up? She went to the auditorium, I think, to go work on stuff, so. Yep. Okay. Remember, right, why do we have to include the plus or minus here? Because we are in an equation setting. We are trying to figure out what values make this equation true. Both positive 1 when you square it and subtract 1 gives you 0, and -1 when you square it and subtract 1 gives you 0. Okay? When you're in the wild, though, right, if you just see, like, square root of 4 just show up, that's equal to 2. Okay, but x squared equals 4, and you square root both sides, that means x equals plus or minus 2. Okay, so that is true if you just see that, but if you have an equation, you get plus or minus there. Okay.
Could you?
Yeah.
When you did that, could you do that with the numerator or the denominator?
If the numerator is equal to 0, that's okay. If the function is equal to 0, it's just a 0 of the function.
Oh yeah.
And in fact, if you did solve that top for 0, it would be imaginary. Because you subtract 1 from both sides, you take square root of negative. Shh. Okay, one more here together, and then I'll have you guys try one on your own. Question for me? So like, so what I'm trying to show there, for example, I'll do it up here because I'm running out of space there. If you see something like this, and you're like, what is that? You would say, oh, sorry, Brandon. That's the idea. Sorry. All right, so we're okay then? Yeah. Okay. Okay. Moving on. So when you have an equation, when you have variables in the problem, when you take square roots, it needs to be plus or minus, or any even-powered root, right? So not just square roots, but any even-powered root. Cube root, we don't use plus or minus. Okay. Fifth root 2. Anyway, so on and so forth. Okay, here. When is this gonna? We don't even have a fraction here, right? We don't have any denominators set equal to 0. Or do we? Because what is cotangent? 1 over tangent, okay? Or if you want to be like really kind of tricky here, you could also say it's cosine over sine. Okay, so you could use, oops, sorry, I'm off my page. There you go. So you can use either one there. Okay? So for what values of theta is tangent of theta equal to 0? Or for what values of theta is sine of theta equal to 0? That's when theta is what? Yep. Sine of theta. Whoop! I just wrote another theta there. Sorry. So yep, sine of theta or tangent of theta. Tangent of 0 or sine of 0 gives you 0. 0 and pi. Exactly right. Okay. So there's our two answers. Okay. There would really be an infinite number of answers here if I did not have that little, 0 to 2 pi business going on right there. All right, you guys try one now. Okay, so you guys find the vertical asymptotes. I'm going to just abbreviate that. Find the VA of f of x equal to x squared plus 2x minus 8 over x squared minus 4. And then don't forget, if you want to check your answer, you can look at your graphing calculator. Okay, so go ahead and give that a shot. I'll kind of mosey around here and check things out.
We're going to go over that. I use a big ball. Look at it in your graph, right? You'll see where you have vertical asymptotes.
Okay.
Yeah.
Why they can't?
Did you wrap it?
Oh, X minus.
Wrap. Yeah.
That gives us a wall.
I didn't say you wrong, I want you to grab it. I don't want you to say you're wrong.
Like, nah, fam, you wrong, dog.
No. I used to, but I remember saying something about that. I remember doing it so many times. I used to say
Oh, what you doing?
But I can just
Look at Mikey's nail sometime. Look at Mikey's nail right there.
Oh, I was about to kill it.
Mr. Wood.
Look at my hands. Oh my goodness. You know you're never supposed to spot that with that
So did you see the graph yet?
Yeah.
So where do you have a vertical asymptote?
-2.
Only. Right. So we're going to talk about. I gave this problem on purpose. Okay. So. Okay. So let's go to. Whoop. Great. Oh, did I take a chance yet? I don't think I did.
Oh my gosh.
Okay, so Drew, what you have to come up with here for your vertical asymptote? -2. Okay, you guys hear that? -2 is your vertical asymptote, and that's it. Okay? You might be tempted. You might be tempted, and because that's what we did, right? That's what we did in the past. We took our denominator and we just set the denominator equal to 0 straight up. No problems, right? And that's why I gave you this one. Is because this one, if you just set your denominator equal to 0, you're going to get 2 vertical asymptotes. But then if you go to graph it, you only see 1 vertical asymptote. What happens? Why is this Why is positive 2 not a vertical asymptote? Yeah,
On
Ryan.
no asymptote, there's like a hole there.
Right, it is a discontinuity, okay? So you're right, it does change, Tyler, it does change the function there, okay? It's a different type of discontinuity though. Because it factors out, that's a hole.
Okay.
This is a vertical asymptote at the x plus 2. Very important, okay? So it's a hole.
So I think in pre-comp we're doing it here, just find x cannot equal this, or x
Right.
so
That's for your domain restrictions.
Okay, so-
Domain restrictions, they're both domain restrictions for sure. They're both discontinuities for sure. They're different types of discontinuities. This is a removable discontinuity, thus you can like cancel it out. This is non-removable, right? You can't really fix an asymptote. It goes to infinity.
So when you're finding a vertical asymptote, you can just actually use factor and call it.
Yes. Yes. In fact, you should look for those things that cancel out like that. So vertical asymptotes are non-removable discontinuities. You cannot fix them. Okay? All right. So that's vertical asymptotes. Now let's look at, what's that? Oh, yes. Sorry, thank you. Bad Mr. Widmeyer.
The belly
You
went
like-
off for you to do it.
You like get yelled at when you don't take attendance? Like
That was me being yelled at.
Oh, I would never take it.
Right, yeah.
They're here, then they're here.
That's right. If they're not here, then they're not here. I was going to say, Emma, I got to take her. Thank you.
But like when we're not here, like later on, Miss Franklin come in and be like, you
No.
didn't take attendance.
Shh. All right, moving on. Next thing. Then we're going to look at limits. So that was kind of ending limits that go to infinity, or sorry, the limits that equal infinity. Now we're going to do the limits at infinity, which is like slightly different, okay? Okay, so consider, all right, let's consider f of x equal to 3x squared over x squared plus 1. Okay. And I want us to find the limit as x approaches infinity of 3x squared over x squared plus 1. And I also want us to find the limit as x approaches negative infinity of 3x squared over x squared plus 1. Okay? So this is the idea where now it's our x that's approaching infinity. Before we were talking about limits that x was approaching like 3, and then the limit was equal to infinity. Okay, but now we're approaching, x is approaching infinity, or negative infinity here. So, if we try and use our typical like tools that we have at our disposal, right, we would try like direct substitution here first. So if I plug in infinity in for the x, infinity squared is infinity, times 3 is still infinity, and I'm dividing by infinity times infinity plus 1, so it's like infinity over infinity, and you're like,
Well, that's just one.
I don't know. That's hard to do. Maybe let's go to our calculator, right? Because when all else fails, we can go to our calculator and maybe try and figure it out that way. So we'll clear out our y1, and let's type in 3x squared, right? And then in the denominator, x squared plus 1. Yeah, don't forget parentheses around your denominator. Okay, always put those parentheses around your denominator. You really should technically, it's not a bad habit to also get into the habit of putting parentheses around your numerator too. Not a bad idea. Just keep it all nice and grouped. What's that? Okay. And so then how can we use our tape, because obviously there's no infinity button on my calculator. Some of the like the newer calculators, or like the higher advanced one, like a TI-89, they have like an infinity command or whatever. But we're not going to do that. Yeah. but we're not going to do that. We're going to try and like mimic approaching infinity. So how can we kind of like mimic approaching infinity using our table here? What can we do? Type in really, really big numbers. That's right. So like 1 with a bunch of zeros.
What?
Or you can do 9 with a bunch of nines. Okay. So if I look here, okay, so what is that? Yeah, 1E9, 1E10. What is that?
1 times 10 to the power of.
It's a scientific notation. Yeah, it's 1 times 10 to the power of 10. Or it's 1 times 10 to the power of 9. Okay? One thing I forgot to mention, like the ABC kids, okay, you guys, when you came in, I forgot to mention this. The calculator will like kind of approximate sometimes when you like type in this many numbers, it'll approximate right. And if you arrow over, it says 3, but when you highlight it, well, actually it does say 3 for sure there. Never mind. Okay, it might not actually go to 3. It might be like close to it, but in this case, it is precisely 3 that they gave it. It shouldn't be precisely, but anyway. Okay, so it's like, wow, this is pretty clear that the answer here. Oh yeah, it'll like overflow the calculator. Yeah. So it's pretty clear that the answer here should be 3. Okay. And then how could we figure out, what about negative infinity?
Tiny numbers.
So we should pick, yeah, really, so like negative 1 with a bunch of zeros. And it also goes to 3. Okay? So since this is true, okay, y equals 3 is a horizontal asymptote. As we go really, because what does it mean to as x approaches infinity? That means as we go really far to the right, our y values are going to go to 3. Like our graph is going to like approach the value y value 3. As we go really far to the left, our y values will also approach 3. So y equals 3 is a horizontal asymptote. Horizontal asymptotes, and this is important, so please make sure you like listen for this, okay? Horizontal asymptotes are not exactly the same as vertical asymptotes. For example, will a function ever cross a vertical asymptote?
No.
No. But a function can cross a horizontal asymptote. That's okay. Okay? It's going, but what a horizontal asymptote is mostly trying to show, it's like end behavior. As you go way far out, it's going to approach that value, in this case 3. Okay? So in fact, let me define.
Wait, so if it crosses the asymptote, then it's not really an asymptote.
A horizontal asymptote can be crossed. I know it. It's because you think, but in this, so if you're going to define it that way, horizontal asymptotes can be crossed. So we do call them asymptotes, but it's not the same as a vertical. It's not the same kind of behavior as a vertical asymptote. Okay. So definition of horizontal asymptotes: the line y equal to L, where L is just a number there, is a horizontal asymptote of f if. So again, the line y equals L is a horizontal asymptote of f if the limit, bless you, as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L. Okay? So that means we could potentially have more than one horizontal asymptote. If our limit as x approaches positive infinity goes to one number, and our limit as x approaches negative infinity goes to another number, then we could have 2 horizontal asymptotes. Okay? We could have 2 different ones there. So, yeah. Questions thus far? Any questions thus far? Okay, then, let's keep going. Okay, so here's a little theorem. This one's not super, like, big. There's no name for it. That's how you can tell, right? If the theorem is named, then that means it's really important. This one doesn't have a name. If R is a positive real number, okay, and C is any real number. So again, if R is a positive real number and if C is any real number, then, oops, sorry, I went off the page there. The limit, as x approaches infinity, of c over x to the r is equal to 0. Okay, if r is a positive real number and c is any real number, then the limit as x approaches infinity of c over x to the r is 0. So let's see that in practice here. Okay, our goal here is to find the limit. Okay. So let's find the limit as x approaches infinity of 100 over x cubed. Okay. So again, in this case, the c that we're talking about here is 100, and x cubed, right? So the r is 3. But what does that have to be? 0. And it kind of makes sense, right? Because if x is approaching infinity, that means x is going to get really, 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 really big. And if we cube a really big number, it gets even bigger. But we're dividing by a huge number, and so that 100 is going to, that overall value is going to get really small, right? The larger your denominator gets, the smaller the value of the fraction becomes. And so it's just eventually going to go to 0 because infinity gets so big. All right, let's try another one. The limit as x approaches infinity of 3e to the negative x. Okay. So we might look at this and think, maybe negative infinity? Because we're going to like imagine like direct substituting in here and it'd be negative infinity. Okay. But e to with a negative exponent, what does that mean? Where does that go? It goes to the denominator, right? When you have a negative exponent, that means this e can be rewritten as 3 over e to the positive x, right? And so then if you can imagine plugging infinity in here for x, what's going to happen to the value of our denominator?
It's going to get very large.
It's going to get really, 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 really big. Oh, here, by the way, one thing I want to really quickly point out to you guys. Pi is approximately what?
3.14.
E is approximately what?
2.181.
Okay, 2.67, I think, or something like that. Let me just check to make sure. I think that's right, though. 2.72, 2.72. Okay, we should be familiar with that. So pi, just a little click aside here, is about 3.14. We should also be familiar with e. It's approximately, I should put a little squiggly lines here. E is approximately 2.72. You should be familiar with that, okay? Just for, mental math kind of calculations, stuff like that. Anyway, this is going, so like a positive 2.72 to infinity power, it's going to get really big, so this also goes to 0. Okay? Because the denominator just gets way too big to kind of, overpower that numerator there. All right, last little one we'll do together, and I'll have you guys try some. The limit as x approaches infinity of 5 minus 2 over x squared. What do we think here? Does this one go to 0? Yeah, no, it does not go to 0, or at least not the whole thing, right? When you have a limit like this, and by the way, it's the limit of the entire quantity here, remember you can break up the limit over subtraction or addition. So here, since I have subtraction, I'll say the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Okay? What's the limit as x approaches infinity of 5?
5.
Yeah, there's no x there. It's 5. Okay? Now, what's the limit as x approaches infinity of 2 over x squared? 0. So it's 5 minus 0, 5 is your answer. Okay? All right. Questions on that? How this go to 0? Because what we imagine here, what we're evaluating for this is we're plugging in a huge number. Sorry, I just talked like Donald Trump there. Huge. Plug in a really big number and square it. 2 divided by that really big number is going to be teeny tiny 0. Okay? All right. You guys, this left half of the room, I want you guys to evaluate the limit as x approaches infinity of 2x plus 5 over 3x squared plus 1 using your calculator. So you guys over here on the left-hand side of the room, using your calculators, evaluate this limit. Okay? Y'all in the middle. Okay? 2x squared plus 5 over 3x squared plus 1. So slight difference for y'all in the middle. Okay? And then letter C.
We use our calculators.
Yeah, please use your calculators, or if you already know it, you can do it that way too. And then y'all on the right. Okay, 2x cubed plus 5 over 3x squared plus 1. So you'll notice there's only a slight variation in all of these. Okay. Okay, so go ahead and do those real quick. Use your graphing calculators. Calculator. Calcu now or calculator? Oh, Emma. Yes.
Just on my calculator.
There's one on my desk in the back.
I literally watched the video last night.
Okay, we ready?
Yeah.
Ryan, what you got for letter B here?
2/3.
2/3. Word. Okay. Let's see here. Josh, what'd you get for yins? 0. Okay, great. Good. And then I need to pick someone over on the other side. Oh my gosh, this is going to take forever now. Alright, let's just go with Tyler. What'd you get for yours? Don't know yet? Don't. Does not exist. What? Okay, so what changed? The degree of this x term, the x term here in our numerator, right? So, what's kind of happening here? It's how quickly our numerator and denominator are kind of like growing, we'll say, okay? So, for example, here in this first one, 2x plus 5 is going to get bigger slower, or not as quickly, as 3x squared plus 1. Why? Because we're taking infinity here and squaring it. Yes, this is being multiplied by 3, and yes, we're adding 1, but those are going to be negligible when it comes to comparing it with the square term there, okay? So this denominator, since it's going to get bigger faster, will make this whole thing eventually go to just 0. Okay, here, since they both have x squared terms, that means they're both going to basically get big at the same time. But you might say, Mr. Winmeyer, though, 2 times 2x squared is smaller than 3 times x squared. And you're right, but when numbers get big enough, it actually, the 2 and the 3 aren't going to matter. They're going to be negligible because you're eventually going to be squaring like 1 trillion, and 2 times 1 trillion squared is not that much different, I know it's hard to believe, than 3 times 1 trillion squared. And the larger it gets, the less that difference is going to make. Okay? And so in fact, these kind of get bigger at the same time, and so we take the ratio here, these lead coefficients. And then last one, the limit is x approaches infinity of this, okay, the degree of the denominator is smaller, so that means our numerator is going to get bigger faster. That means this thing overall goes to infinity, which means does not exist. Okay? We talked about this back in pre-calculus, or you should have at least, all right? I'm going to try and quickly write some guidelines down here, and we'll see if I can get it in. All right, so guidelines for finding limits at infinity for rational functions. Ooh, that's a lot there. At infinity and beyond. Okay. Okay, so it all has to do with the degree. Remember, the degree is equal to the highest powered term. Okay, so 1. I'm going to abbreviate here. If the degree of the numerator, I'm going to abbreviate numerator num, degree of numerator is greater than the degree of the denom, okay, limit does not exist. Okay. 2. If the degree of the numerator equals the degree of the denominator, okay, it's the ratio of these lead coefficients. So 2 over the 3 there for letter B's case, ratio of lead coefficients. Okay, is the limit. And finally, if the degree of the numerator is less than, the only other option that we have, than the degree of the denominator, okay, the limit is 0. It looks like a heart the way I drew it there. Okay, 0. Okay. All right. No, we're gonna have some homework. I had a little bit more I wanted to show you, but that's okay. I think we should have enough done to be able to get the homework in.